we have a beam that runs 20 meters. So we have a beam that's spanning 20 meters long, and it has two supports, or what we can call walls, in between the edges of the beam. So I think we have to kind of like be a little bit more generous with these lines. So this is 20 meters. That's the total length of the beam, and it happens to have two walls. The first one, we're going to call that A, wall A, and then the second one is wall B. Wall A is a distance of 3 meters from the left edge, and that left edge, we're going to call it C. This is wall B. And then the right edge, we're going to call that D. In between the walls, there's a distance of 12 meters. And something else happens is that the weight of the wall, or rather the weight of the beam, will be hanging at the middle of the beam at 10 meters from the edge. So from this side, from the left side, it's 10 meters, and also from the right side it's 10 meters. So this distance right here from the left edge D up until the center, that's 10 meters, and the distance from wall B up until from wall B up. So if this distance from right here up until here is 10 meters, and this total distance, so this whole distance up until here is 15 meters. So from the left edge C up until the wall B, that distance is 15 meters. It simply means that the distance from B to D is going to be 5 meters, because the entire distance is 20 meters. So the other distance of interest is from the center up until wall B. That's going to have to be 5 meters. Why? Because if this distance is 5 meters from D up until B, and the distance from the center right here up until D is 10 meters, that means the distance from the center up until B is going to be 5 meters. So these are just algebraic simplifications. This is the first thing about the problem. So these are the distances we're given. The other piece of information that we're given is the fact the beam itself, assuming the mass of the beam. Well, we don't know what the mass of the beam is, but assuming the weight of the beam, WB, is 650 newtons. That's the weight of the beam. And so the first part of the problem is that, we want to find the maximum weight. Of someone. Let's say someone stands right here at D. So we have a character that stands at D. So we want to find the maximum weight acting downwards. We're going to call that W max. That's the first thing. That the maximum weight without the beam tipping. The beam is just about to tip, so we want to find, what's this maximum weight, calling it W max. If they're stepping right here, it means the beam is about to tip. So that's the first part of the problem we want to find out. The second part of the problem is we want to find the forces FA and FB, the forces exerted by the walls on the beam. So this would be FA and this would be FB. Those are the forces we want to find out, the two forces. And then we want to find those forces, when the person is standing at D, and then when standing 2 meters to the right of A, 2 meters to the right of A. So, I mean, there is a lot of information about this problem. 2 meters to the right of A, that's going to be, round about this point right here. So this is the second part. They're going to be standing right there. And so, what that distance is going to be 2 meters. Obviously, if that distance is 2 meters, it means that up until the point, this distance is going to be 10 meters. Okay, because the entire distance is 12 meters. So those are the pieces of information we're given. We're going to start with the first one, where we want to find the maximum weight of the character. Remember, the system is in equilibrium just before it tips. And therefore, the sum of torques about B is going to be 0. And so the weight of the beam, remember the beam is, this one is pointing downwards. This weight is pointing downwards. So relative to B, it's going to be counterclockwise, and therefore will be positive. That weight of the beam times that distance, which is 5 meters. This distance, remember we said, is 5 meters from B, times 5.0 meters, minus the maximum weight when the person stands at D. They're going to be off a distance of 5 meters also. That's going to be 0, because the sum of the torques is 0. And so in the next page, we start plugging in numbers to solve this problem. We know that the weight of the beam is 650 newtons, 650 newtons. So 650 newtons times 5.0 meters minus the maximum weight times 5.0 meters. That gives us 0. So we can solve the maximum weight to be 650 times 5.0 newtons, or rather meters. This is 650 newtons, all over the 5.0 meters. These two cancel. So we get the maximum weight to be 650 newtons. That's the maximum weight at D. And that's the first part of the problem. The second part of the problem, we're going to do that in the next page. And we want to find the normal force at A. Remember, in a simplified version, this is how it looks. We have A, we have B, and then we have D. If the person is exerting a maximum force right here, what's going to happen is that the beam is going to tilt. It's going to tilt just a little bit. It's going to tilt right there. And so, they're stepping down that way. It's going up. The moment it tilts, you notice that we don't have any force acting at A because the beam is no longer touching the wall. So that means the force at A is going to be 0 newtons. That's the force at A. Remember, the force at B, the force at D, maximum weight of the person is 650 newtons. The force at A is 0 newtons. And so this point B now supports the weight of the person and the weight of the beam. So B supports those two weights. And so the force at B, becomes equivalent to the maximum weight of the person plus the weight of the beam, because the weight, there is no force at A, so all the forces are being concentrated at B. So the maximum weight of the person is 650 newtons. The beam is also 650 newtons. So the force at B ends up being twice that amount, so that's 1300 newtons. So, we've found the maximum weight of the person. We've found the force at A is 0. The force at B is 1300 newtons. And then in the next page, now we have a different scenario. So, we still have the beam. It's like that, but this time this is B, this is A. The person right now stands 2 meters from the edge. This is 2 meters. And so this distance is going to be 10 meters. Okay, that's 10 meters. We're still taking torque around B. And so the sum of the torques around B will be 0. There is the weight of the beam, which is counterclockwise, so that's going to be positive, the weight of the beam. And this distance, if you can recall, was 5 meters. Going back to the beginning, that distance was 5 meters right here. And so we're going to include that in the problem. Okay, we're going to include that in the problem. So this distance right here, this is 5 meters. And so the weight of the beam times 5 meters, that's positive because it's counterclockwise, plus the weight of the person or we call it the maximum weight of the person, times this distance. So, we're saying from this position up until that position is 10 meters. We're going to include that 10 meters. And since the weight is pointing downwards, it means that the torque for that weight around B is also counterclockwise, and therefore it's going to be positive. But also we need to find the force at A. So the beam A is pushing upwards now, which means it's going to be clockwise, and clockwise is negative, and that's why we have negative FA. This force right here is FA. And just going back to clarify, you can see this was FA and this is FB. And so the distance of A up until B is 12 meters as given in the first page. This is 12 meters, you can see. So coming back, we multiply that by 12 meters, and that sum is 0. Our goal is to solve for A. So f of A, you can see, becomes the beam, weight of the beam times 5 meters plus the weight, the maximum weight of the person, times 10 meters. And then we want to divide that, obviously, by the 12 meters. Next page, we're going to start plugging in the numbers. So we end up getting f of A equals to 650 newtons times 5 meters. And then plus 650, which is the maximum weight of the person, times 10 meters, which is the distance from B. And then we want to divide by the distance from A to B. And that gives us a force of 810 newtons. That's the force that A exerts right here. This force right here is 810 newtons if the person stands a distance B from A, from the point A. And then the next thing that happens is that now, if you think about the beam, you know, A is pointing upwards. So f of A is pointing upwards. The weight of the beam is pointing downwards. F of B is also pointing upwards. And then we also have, so f of A, f of B, and we also have the person itself, the person standing here, and they're pointing downwards. W max. The system is in equilibrium, and therefore all the forces, the sum of the forces in the y is 0. That means that f of A plus f of B minus W max minus W beam equals to 0. And so f of B has to equal W max plus W beam minus f of A. Plug in the numbers, we get W max, so 650 newtons plus 650 newtons minus 810 newtons. And so f of B becomes 490 newtons. F of B becomes 490 newtons, and this is what you get when the person stands 2 meters from A. So once again, you know, in this problem, it was a beam problem, a beam spanning 20 meters, and with the weight at the center of 650 newtons. That was the weight. The beam was supported by 2 walls A and B, and the walls were pushing up was F of A and F of B. And also we wanted to find the maximum weight of the person right here if they're standing right here. So they're pushing downwards. It's just about to tilt. And so the torque around B will be 0. The beam is pushing torque in the counterclockwise direction, so it's positive. And then the person is pushing in the clockwise direction, so it's negative. That sum is 0. In the next page, we plug in the numbers and get the maximum weight to be 650. We want to find the force, the reaction force at A when they're pushing downwards. You can see that at A, it's just barely touching, so the force is going to be 0. But then at B, there is a force which is holding on to the weight, resisting the weight of the beam and the weight of the person. That's why these two 650s add up to 1300. That's the force supported by B. And then also we move the person so that they're 2 meters from A, and so we use the sum of torques being 0. And the torque due to the beam is going to be positive because it's counterclockwise. The torque due to the person is going to be also positive because it's counterclockwise. So it's going that way. The torque due to A will be clockwise, so that's going to be negative. And then we simplify for A. So in the next page, we end up solving A to be 810 newtons. Finally, the equilibrium in the Y is 0. So we introduce the force due to A, the resistance upwards, plus the force due to A, the force due to B. Those two are positive because they're pointing upwards. And then the weight of the person and the weight of the beam are pointing downwards, so those are negative. And we rearrange the problem while focusing on B, solving for B. We got 490 newtons. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.